Hello, this is Jennifer Martinez, and in this video we're going to look at the definition of the derivative. We're going to see where it came from, and then we're going to visualize it. Let's start with the definition in the book. The derivative of f at a point A is written f prime of A is defined by the rate of change of f at A. By the way, this is instantaneous rate of change. When they don't say the word instantaneous, they do not mean average, they mean instantaneous. And it's defined as the limit as h goes to 0 of f of A plus h minus f of A all over h. So to see where this came from, we're going to look at the average rate of change. From the last section, we saw the average rate of change was the change of y over the change of x. We'll call this y here. And what I'm going to do to see this formula here is I'm going to let point A be the point A here. And so we know that the y value is f of A. And point B, I'm going to let be A plus some h, right? Some small value of h. So this would be A plus h, and that f value is just f of whatever that x is, A plus h. And so now if I look at the difference between these two, that's where they get f of A plus h minus f of A all over h. And by the way, that is the slope of that secant, they'll call it, line. Sometimes they'll call it the slope of the secant. And if we let those h's get smaller and smaller, we'll come up with an instantaneous rate of change, or just the rate of change, as these h's become smaller. To see the visual of that, here it is here. So this was what we started with. And then we're going to do a little smaller h, right? A little smaller h, a little smaller h. And you can see that that derivative is going to be turned into the slope of the line. Sometimes they call that the slope of the tangent line. So I'm making this a little smaller so we can see everything on one screen. We can see that the slope of the tangent line is going to be the instantaneous rate of change. So we just can call that the rate of change of f at x equals a. And what is it going to be? It's going to be the limit as h goes to 0 of our average rate of change that we have here above. And again, that could be called the slope of the tangent line. So there it is. That is the definition. You can see that they got here. This is what we're going to call f prime. You can also call this f prime of A. Or if you rather, you can call it the instantaneous rate of change. And again, this is written as f prime of A. Okay, let's look at an example of this. Example 4 in the book. Estimate the value of the derivative of f of x equals 2 to the x at x equals 0 graphically and numerically. So let's start with graphically. So what they did here is they decided to choose -1, 0, and 1. I'm going to start with 0 and 1 because we know at 0, we know this is just 1, and at 1 it's just 2. So you can easily find the slope of those 2 points. Again, I'm going to call this y. So we know that that's going to be 2 minus 1 all over 1. So I'm going to use that average rate of change to get 1. So that's the slope of the secant of 0, or the slope of the secant between 0 and 1. This line right here, that slope. There it is in red. So I'm going to call that the slope of AC. So then let's take the slope of BA. because we know -1, that would be 2 to the -1, or 1/2. So we can do that. So we're going to have 1 minus 1/2 all over 0 minus -1. Again, new minus old, new minus old. So it's going to be 1/2 over 1, so just 1/2. So that is that line between B and A in green right there. So we know that the slope of the tangent line, that instantaneous velocity, has to be somewhere between. It's a little steeper than the green, but not quite as steep as the red. So maybe a good estimate would be the average, 0.75, but we know it's between there. So it's between 1/2 and 1, or if you take the average, it's approximately maybe 7.5 from the graph. So can we do better? How would we do better is we would choose values closer, right, than 1, as we did above here. So that's what I'm going to do numerically. So here's a table of some values of h. What is h? I'm using the formula that we did above here before taking the limit, that average velocity formula. And I got that again. My h is somewhere closer. I don't know where. I'll call that h. That's 0. So this would be, I'm going to make it, my a is going to be 0 in this case. So I'm going to really make this f of h minus f of 0 all over h. So that would be my values of h. So for instance, if we're going to look to the right here, if I look at h being 0.001, look at how close that is to 1. 1.4 zeros, and then 6932. That would be the value if I plugged in that h, which in this case, since a is 0, is the same value of x. So if I plug in here 0.001, I get this value for my y. So if I subtract those and do this, you would get a closer estimate. So what they did here in this last column, they just figured out 2 to the h is f of h. And then f of 0 we saw here was 1. So that way we can look at this in general, numerically. So when I plug in the value here, this is going to be, so at h being 0.0001, we get that the delta y over the delta x, this quotient, right, to the h minus 1 over h is equal to 0.693171. And you can see that if you did the ones to the left, it's very similar. We can now take the average of those two, right? Because then what I did before is looked at the negative side, negative 0.0001, and 0, like I did -1 here, and it would be the average of those two values. So it looks like a pretty good estimate. It has to be that f prime of 0, which by the way is the limit as h goes to 0 of f of 0 plus h, since our a is 0, minus f of 0 over h, which we just concluded is this. And we have a table here saying that these values are equal to 0.693. So that would be the instantaneous rate of change, or the derivative, at x equals 0. Now the reason that this actually is still an estimate, I can change to an estimate, because we're going to find out later that if you look at, and want to find out this exactly, it's actually going to be ln of 2. You can see that ln of 2 on your calculator is 0.693. So that's why it's actually, in this case, an estimate. But a pretty darn good estimate. We got 3 decimal places worth of accuracy. But we'll see this in chapter 3. So now we can do example 5, which is find the approximate equation for the tangent line to f of x equals 2 to the x, which is the same above, at x equals 0, because we also know that this is the slope of the tangent, and that's what we want. So we can, and we had the point, if you remember above, if you plug in 0, we know 1. So we have the slope and a point. We now can find that tangent line, y minus 1. Slope is now 0.693, x minus 0, which, by the way, is just, I'm going to put a 3 there, but that's okay. And we could actually use y equals mx plus b and found this straight away. But there it is, 2 decimal places worth of approximate. So I will make that an approximate value here. So it is an estimate, but many times this value will be exact. And since we recognize that 0.693 was ln of 2 up here, you could, if you wanted to write it exactly, we'll see this again in the next chapter. Wrote it like this. But they did ask for an approximate equation, so you don't need to do that. Just so you know, if this was a repeating pattern, like say it was 0.66666, you would have said, oh, I recognize that exact value. That's 2/3. So this is going to be the exact value, that limit. On this one, 0.693, if you knew that number offhand was ln 2, that's when you could write this. Otherwise, it's 0.693 is a fine answer.